Okay, so today I want to wrap up the section on radial composition. So that next week we will start talking about symmetries and the relation between symmetries and observed quantities, what we know Lorentz theorem. So we're mostly going to be focusing on the quantum version of Lorentz theorem, but I will spend some time talking about what symmetries are, what types of symmetries they are, and how they code physical properties of the system. So today I want to talk a little bit more about the couple of technical details that largely revolve around the idea of conformal dimensions. And conformal dimensions are related to the dilatation operator in the same sense that I said that energy eigenvalues are related to the Hamiltonian operator. Okay, so we'll define this in a little bit, and then we'll use it to define a set of operators and special field theories. Namely primary operators, formal primary operators, and their descendants. But first, I'm going to say a little bit more about radial conjugation and a formal way of defining this conjugation. And I'll show you that written in a particular way. These conjugation relations are kind of similar to things you've encountered already in quantum mechanics, namely the harmonic oscillator algebra. So we learned the last time that given some operator, some Heisenberg operator, let's say A is a function of tau, this is a Heisenberg operator in Euclidean space. The Euclidean conjugation, A double dagger, of A was A dagger evaluated at minus. So I wanted to get correct unitary properties of this operator of let's say the time evolution operator in Hamiltonians in Euclidean space. Then what I needed to do was define the conjugation in this way. So to do normal traditional conjugation, but then I replaced tau with minus tau. But we know also that the radial variable r is defined to be e to the tau, tau is a Euclidean time. Follows that under Euclidean conjugation, R goes to 1 over R, because tau goes to minus tau. In other words, radial conjugation is accompanied by an inversion. The adjoint of some operator, let's say O, is O double dagger is O dagger conjugated by inversion. Right, so inversion, O dagger, or condition conjugation, inversion. So this guy here, I is an inversion operator. That takes x mu to x mu over x squared. Okay. this is what inversion means for operators. Sorry, for conjugation meaning for operators, but we also have states that live in the Hilbert sphere. And for those, if I have a state psi in my Hilbert sphere, I'm going to take the Euclidean conjugate of this, then this is the Hermitian conjugate of psi, which takes the get to the graph. The same, but yeah, this is how we define conjugation states. So as an example, let's do a sanity check. So let A is some Hermitian operator. In the Schrödinger picture, that is to say, the time evolution associated to A states in this picture involved. The associated Heisenberg operator is A of tau, sorry, T. A of T, I get by taking e to the I H T, A e to the minus I H T. So given some operator A, which I'm assuming to be the Schrödinger picture, I can construct a time-dependent operator A of T by multiplying on the left and right by the time evolution operator. Okay. All right. So let's see what happens if I conjugate this guy with the usual emission conjugation. So if I find a dagger, T, this is e to the minus H T, A e to the minus H T, all conjugated. Conjugation of A B is B dagger, A dagger. So this is just e to the minus H T dagger, A dagger, e to the I B dagger. The Hamiltonian is necessarily Hermitian. We don't do anything to T, and under the dagger operation, I goes to minus I. So this is just e to the. This is just e to the H T. A is assumed to be Hermitian. So that's A e to the minus I. H T. Which is just e to the minus just A. Right. In other words, if I start off with some emission operator, showing a connection, associated Heisenberg operator is also emission at the same conjugation operation. Okay. So this is the new cosmos space. What about Euclidean space? So given that emission operator there is something the Heisenberg operator in the Euclidean space is A of tau, which is beta H tau, A minus H tau. So now if I take the emission conjugate of this, so A dagger of tau, this is e to the minus H tau dagger, A dagger e to the H tau dagger. Is e to the minus H tau. A e to the H tau is just A of minus tau. So if I want to correct Euclidean dagger, now what I have to do is replace tau by minus tau. A double dagger of tau is a dagger of minus tau. Since a dagger of tau is a minus tau, this is this A of tau. So we reproduce the correct daggering properties. We use the correct dagger and you do this. This is why I talked on about this. Euclidean conjugation. Okay, so now I want to make one final point that's particularly interesting a bit further, which is to see how this relates to the algebra of raising and annihilation operators, raising and lowering operators with harmonics. Okay. So, how many of you have seen the harmonic oscillator before? How many of you have seen the harmonic oscillator before in raising and lowering operators? So, I would like you to recall that ladder operators of oscillator satisfy the following algorithm. If I calculate a commutator with the harmonic oscillator Hamiltonian, I get back A. In fact, this feature is used to define coherent state of the harmonic oscillator, which are the kind of most classical quantum states. Similarly, if I take the dagger, emission conjugate of this thing, then I will find that, again, using properties of the dagger operation, that A dagger H, A dagger commutator H is minus a dagger. And this observation that the commutator of a with a dagger with a minus a dagger is enough to allow us to show, we normally do this in a first class of quantum mechanics, that A lowers the energy of a state by 1 unit, and a dagger raises the energy of the state by 1 unit. That's why they're creation and annihilation. So back on the vacuum of A, that it's annihilated, and I can produce solid states by acting with a dagger. The reason I want to mention this, I'm going to describe this down. So from here, that A effectively lowers, effectively raises energy of a state by 1 unit. So the point I want to make here is that anywhere I can find a similar structure, if I identify the appropriate operators, then I'll have the same properties holding for those operators. Something raises or lowers something by some unit. And the point is that there's a similar algebraic structure that exists on the field theory. And all we have to do is identify the appropriate operators that play the role of the raising and lowering operators in the CFT. So let me do that for you now. And the first point I want to make is that something similar happens in conformability. Let me show you why. So we'll start from the following fact. This is that if I take the momentum generator, P mu, and I take the Euclidean conjugate of P mu, then following what goes on here, this is just I P mu dagger I which is I P mu I, because this is and I also have a representation for the PPU generator as a derivative operator. This is just I standard time the mu I. And if I put some test coordinate in here, x mu say, x mu here, then I have the property of converting that like this, and then I have to act with the derivatives, and then I have to invert again. So the upshot, I'm going to give you guys on the next slide, is that this is just sorry, the minus one. this is just minus I times x dot x squared, I mean x v, right? d minus 2x, say beta, x d beta. Then I go back to my representation for the operators, generators, and I recognize that this thing is nothing but K. Generator of critical conformal transformations. This relation here tells us is really a statement about how derivatives transform under the conjugation, the Euclidean conjugation operation. Okay. Okay. Next point is to see what happens with the differentiation generator. So if I take a differentiation generator and I take its Euclidean conjugation, then this is just I dagger I, which is just I x nu x nu d mu. But I know what I does to x mu. So this is just I x mu over x down to x I d I. And I've just learned what I d I does, because I know now how derivatives transform. So this is just I times x mu over x dot x times x dot x d minus 2x beta x mu beta. So this x dot x cancels with this one, and that's just pi x mu d. I have x dot x here, I have x nu here, so this is the same as x dot x. So that x dot x will cancel that one, and then I have a minus 2 x beta d beta, but beta mu cares. This is just minus I x mu d mu. But I x mu d mu, that's just the third of the rotation generator, minus d. You guys, we have tried so hard to do this question in the test. Actually, we're on the 100. And this. Does it make it clear or does it? Okay, this one is clear. Figure out the top one. All right. But then the next step is really. So similarly, but with some more tedious work, you can show that if you take the Euclidean conjugate of K we get P and the M new generator of course, is just okay. Yeah. Now there's a point to be made about this guy. The fact that D double dagger is minus D and not D tells me that this dilatation generator is anti-emission under the Euclidean conjugation. Right, so this is a statement that this guy is anti-emission with respect to double dagger operation. Which in turn means that if eigenvalues are going to be pure imaginary. So eigenvalues of D are imaginary. So if I want real eigenvalues of D, I want something that has real eigenvalues, then I need to consider instead of T, the operator I. And these guys are going to have completely going to be purely imaginary, then I will have real eigenvalues. Okay. So now let's cycle back to a statement about the harmonic oscillator. Or in fact, let's go via the formula. So from the formal algebra, we know the following. We know that if I take the commutator of D and T, T and E, then I get minus I D mu. And I also know that the commutator of P and K is I K. So now let's write everything in terms of ID instead. So I D with P is E mu, and ID with K is minus. Okay. Now let's go back up to the harmonic oscillator algebra 1. Okay, and note that P mu conjugate is K mu, right? And K mu conjugate is P mu. The same way that A conjugate, emission conjugate, is A dagger, and A dagger conjugate is A. Okay, so now you can see that if I identify A with ID, if I identify H with ID and P mu with A, K mu with A dagger, then this looks, well, it is the same algebraic structure under that conjugation as the harmonic oscillator. So what this means is that we would expect, in the same way that we found, that we know that A and A dagger lower and raise the energy of a state by 1 unit, and the energy is just the eigenvalue of the Hamiltonian. I would expect that P mu or K mu raise or lower the dimension of some state by or operator by 1 unit. So let's check this. So the observation here is that this is compare 1 and 2. with the appropriate identification. So let's check this. So what I want to do is I want to show that when P mu acts on some state with some definite conformal dimension, that it raises the conformal dimension by 1. So the first thing I need to tell you is what do I mean when I say an operator? What do I mean when I say that a state has a particular conformal dimension? So we will say that a state let's say delta has conformal dimension delta if delta is this delta is an eigenvalue of I times the limitation operator and the corresponding eigenstate is delta. Okay, so if I t acting on delta the number times the state of delta. This is not state. The delta space, and this is a number. So that's what I mean when I say that a state has a conformal dimension delta. So then we should ask, what is the conformal dimension of the state that I get when I act on this state of P mu? So the question is, what is the conformal dimension of state P? Well, that's easy enough to find out. All we have to do is act on that state with the operator ID. So ID acting on P delta is ID P delta plus P mu by d delta minus P mu by d delta. So all I've done here is add and subtract the state P mu by d delta. Okay. So this is 0, but I know that these two combined is just the commutator of ID with P mu acting on the state delta, and then I can subtract off this P mu by d delta. ID P mu is just P mu. So this is just sorry, we will sign it back. It's these two that are commutator. That's just P mu acting on delta plus P mu acting on ID acting on delta is just delta. So that's delta, which is number times delta. So this is just delta plus 1 P mu In other words, if the state delta had eigenvalue delta with respect to IG, then the state P mu acting on delta has eigenvalue delta plus 1. So my claim that P mu acts as a raising operator, in this case raising the conformal dimension of the state, is valid. Moreover, an operator, let's say let O sub delta, has conformal dimension delta if it satisfies that the commutator of ID with this operator is delta times the operator. So if ID commutator with O delta is delta times O delta, then there is such a statement should not be surprising given the state operator corresponds. Okay. But let me show again that at the level of the operator, the statement that P mu is a raising of a conformal dimension operator still holds. So in particular, if we calculate the commutator of ID with P mu multiplying the operator of dagger. I say multiplying, it's really P mu acting on O acting on something. This is just ID P mu ID commutator with O plus ID commutator with P mu. Oh, this is because, as we learned in the differential geometry course, the commutator is a derivative, so it satisfies the Leibniz property of derivatives. In other words, the product. Well, I know that O has conformal dimension delta, which means that this is just delta P mu O delta. And then the other ID commutator of P mu is just P mu O delta. So again, this is just delta plus 1. Okay. So let's go back to the harmonic oscillator story. You will remember that instead of all states of the harmonic oscillator, one of them is better than the vacuum state. The vacuum state is a state of the lowest energy, not necessarily zero, the lowest energy. But not only does it have the lowest energy, it's also annihilated by A. Right? And we're trying to build an analogy of what's going on here. And the analogy is what's called the conformal primary. The conformal primary is that operator with the lowest conformal dimension, and that is annihilated by K, because the conformal generator K mu plays the role of A. Okay. So a conformal primary state. So, control primary operator. Is that operator with lowest formal dimension and annihilated by special formal generator thing. And states that are obtained from the conformal primary by acting with P mu, the raising operator. So I find a state that has the lowest value of delta, and then I raise from there by acting with P mu. These are all called descendant operators. And what we're going to learn shortly is that conformal primary operators, their dimensions, their spins, constitute the basic data that you need to study any or properly define any conformal field data, right? So what we're going to be building towards is something called conformal bootstrap, which is the process of identifying what the basic data that I need to fully specify any conformal field theory. So what we're going to learn is that if I give you all the conformal primaries of theory, plus their spins, plus their conformal dimensions, then that's it. You can probably define any conformal field theory. So operators and from the primary by acting with mu are called okay, so that's all that I wanted to say about radio conversation. And I will upload these now. And we'll also upload the next exercise sheet sometime this weekend. Okay. And then we'll basically cover radio conversation and some aspects of some G's. All right. Cool. Okay. I was thinking you would do the same way that I did the take home down, or I'll give each of you a Dropbox and you just upload it to the Dropbox. Does that work? That way I can speak back to this stuff. Yeah. Huh? By midnight. You can even do it by tomorrow. Sorry. I really don't. I'm not fussed about the hand in, but I will have in the drop